Hello everybody, I welcome you all to NCAS Geology class. Today I will discuss about the physical properties of minerals. So before we discuss what is a mineral, let us know what is a mineral. Mineral is a naturally occurring homogeneous substance which has more or less definite chemical composition and definite atomic structure. And these are produced by inorganic processes. These are the three properties of minerals. They must be inorganic in nature, they must have more or less definite chemical composition and atomic structure. So these properties can be studied based upon their state of aggregation, based upon the properties of their properties on the basis of light, passage of light through them, or by reflection of light over their surface, then based upon density, based upon electrical, magnetic and radioactive properties, based upon senses, and based upon their reaction to heat. So on this basis the properties have been classified, and on the basis of aggregation we can study the properties such as form and habit, pseudomorphism, polymorphism, hardness, tenacity, fracture and cleavage. On the basis of light we can study the color, luster, transparency, phosphorescence and fluorescence. On the basis of density, or we can say it is the study of specific gravity of the minerals. Then on the basis of electrical properties we can study the passage of electricity through the minerals, or how the minerals display their electrical property, magnetism and radioactivity. Based upon senses we can study the minerals on the basis of their taste, odor and feel, and we can study the minerals, their fusibility based upon their reaction to the heat. So these are the properties which are to be discussed in this lecture. So let us start the properties which are based on the state of aggregation. What are the physical properties? Let us discuss. So let us discuss the form or habit. It speaks about the shape of the crystals. Habit speaks about the general shape of the crystals. The shape which the crystal always generally assumes. So, what are these forms of minerals? Let us discuss. Crystallized. This speaks about where a property when we see that mineral is fully developed along with all its sides. If it is a cube, if it is a galena, it is in form of cube, and cube is fully developed. So there we can say it is a crystallized mineral. If crystalline character is not fully developed, it refers to confused aggregate of imperfectly developed crystals, then it can be said as simply crystalline. But when it is crystallized, it shows well developed crystals. Then cryptocrystalline. What is cryptocrystalline? Here the crystals are not highly developed so that they can be identified in naked eye. So they possess mere traces of crystalline character which can be identified under the microscope. Then massive or amorphous. Here the mineral specimen lacks crystalline form. Amorphous means it is not crystalline. It is not having proper atomic arrangement so that the crystalline status of the mineral can be established. So amorphous means it is non-crystalline. For example, flint, jasper, these are generally amorphous substances of silica. Cleavable. When you talk about cleavable minerals, so the property such as cleavage. Cleavage is the property of a mineral by virtue of which the mineral breaks, producing plain, smooth surfaces, which are ultimately controlled by the atomic structure of the minerals. For example, mica, calcite. Calcite possesses 3 sets of cleavage, mica 1 set of basal cleavage. So, cleavable means the mineral breaks along directions, producing plain, smooth surfaces. When we talk about granular or saccharoidal, it is mostly sugary, or we can say equal size grains. Size is about 2 mm to 10 mm, and it is found in case of chromite, marble. The minerals are found to be granular. When we talk about compact, it refers to a very fine grained minerals where state of aggregation is not obvious to the eye. In our naked eye, we cannot see that the crystalline character is displayed by the mineral surfaces. So, there we can say it is compact. It refers to the uniform aggregate of exceedingly minute particles like those of china clay. China clay is earthy. Kaolin, earthy minerals. So these are the some of the size terms. Equant, that means equidimensional. Here it is, this is the C direction, this is A direction. So A by C, increasing A by C, that means this is A direction, this is C direction. Increasing A, decreasing C. So in this manner, we will get equant, we will get prismatical columnar minerals, we will get acicular, which is fully elongated, as we find in case of sillimanite, capillary or filiform, fiber-like, that means they are fully elongated along A directions. So that the increasing A by C ratio will be there from equant to capillary or filiforms. And similarly, if we go down along this direction, we will get the increasing B by C. So this is C, this is B, this is C. So B is increasing, because of which the minerals become platy, bladed, tabular. So on this basis, on the basis of their axis A, B, C, we can classify the minerals as equant, prismatic, acicular, capillary, tabular, bladed and platy. So in case of equant, the shape of the crystals approach to that of a cube or sphere with crystal dimension A is equal to B is equal to C. When it is tabular, the shape is like that of a tablet or diskette like, with broad flat surface as we find in case of feldspars, wollastonite. Wollastonite is otherwise called as tabular spar. So here A is equal to B greater than C, with C very thin. When we talk about the tabular minerals, when it is equal, the A is equal to B is equal to C. So in 3 dimension, it is equally developed. When you talk about platy minerals, it is sheet-like. A is nearly equal to B, which is greater than that of the C. C is very, very thin. When it is prismatic or columnar, pillar-like, column-like, slender and stubby, where A is greater than B, which may be equal to C. As we find in case of amphibole, beryl, the prismatic or columnar habit. Bladed, it is found in case of kyanite, it is knife-like, where A is greater than B, greater than C, kyanite. Acicular, it is needle-like, slightly thicker than filiform. So A is greater than B equal to C. B, C are very thin. As we find in case of sillimanite, petrolite, these are acicular. Similarly, capillary filiform, it is hair-like. A is greater than B equal to C. B, C are extremely thin, so that A is very, very big. Filiform is mostly wire-like, twisted like strands of a rope, as we find in case of native copper or silver. Fibrous. Here there is parallel arrangement of acicular or filiform crystals aggregates, as we find in case of gypsum, amphiboles, asbestos. So asbestos, the term asbestos is applied to a number of minerals which are highly fibrous, and fibers are noted for their strength, because of which they are used as the minerals of asbestos. Similarly, radiating, here acicular filiform crystals, they radiate out from a common center, as we find in case of stibnite. Divergent, here the prismatic crystals diverge from a common area, as we find in case of stibnite. Similarly, reticulated, here there occurs a lattice work or net-like arrangement of tabular and bladed crystals and needles, as we see in case of rutile. Roseiform, this is rose-like, petal-like arrangement of tabular or bladed crystals. Drossy, it is surface lined with very small goosebump-like crystals. Size generally less than 2 to 3 mm. As we see in case of pyrite, that grows on the surface of calcite. Dendritic or arborescent. Here the minerals, they occur like that of a tree with branching network of crystals. As we see the dendrites of manganese oxide. So it is showing tree-like branching. The minerals shows tree-like branching. Lamellar or foliated or micaceous. Here there is subparallel arrangement of thin leaf-like layered minerals, as we see in case of graphite, mica, gypsum. They are said to be lamellar, foliated or micaceous. Similarly, we have lenticular. Here the crystals are flattened balls or pellets that are shown by concretionary or nodular minerals, lenticular, needle-like. banded. Here the mineral shows thin, roughly parallel layers with different colors. As we see in case of agate, chert, hematite, there is banded structure. Banded structure is displayed by different colors. Concentric. Here mineral shows spherical to subspherical layers arranged in parallel position with one or more centers, as we see in case of malachite. Then botryoidal. Here the crystals are arranged like a bunch of grapes with rounded prominences that are smaller than that of the mammillary types. So it is resembling to that of a bunch of grapes, as we see in case of chalcedony, prehnite, syllabilene, smithsonite. So this is botryoidal, bunch of grapes. Globular. The mineral surface is presenting little spherical or globular bodies. Reniform, kidney-like. Here the mineral surface is like that of a kidney or rounded. So as we see in case of hematite, hematite is otherwise called as kidney ore. Coliform, the term colo means cementing or welding. This form is applied collectively to botryoidal, globular, reniform and mammillary. In case of mammillary, the external form is rather large, rounded prominences or breast-like as found in hematite, goethite. That's why it is like that of botryoidal, but the crystals are rather bigger in size. Amygdaloidal. Here the shape of the grains of the minerals are almond shaped or spherical to ellipsoidal and that fill the vesicles. Amygdals are the vesicles which are filled by the mineral matter. Vesicles are found in the volcanic rocks that represent the surface of the volcanic rocks from where the gases escape before consolidation of the lava to give rise to volcanic igneous rocks. So those cavities or vesicles are being filled up by mineral matter and that is called amygdaloidal structure. Stalactitic. It refers to mineral deposit from dripping water. Thus it shows columns, cones, cylinders of minerals hanging from ceiling of the caves, as we see in case of limestone caves. Limestone caves shows this type of structure from the ceiling, this type of structure from the base. So this is stalactite, this is stalagmite, stalagmite from grounds, from ceiling, stalactite. Both may join together to give rise to dripstones, columns. So stalactitic, that is found in case of limestone caves. Concretionary, it has a center, say a clay core, around which there occurs a deposition of calcium carbonate in form of spherical, ellipsoidal or irregular layers or nodules, concretions. Concretionary, it must have a core, clay core around which calcium carbonate is found to be deposited. Geode, it represents crystal aggregates produced by partial or complete filling of a subspherical cavity as crystals proceed from the walls of the cavity inwards. So these are the cavities. So the cavities are filled up by mineral matter. First lining will be there, then the growth of crystals will be from the walls into the center of the cavity. The minerals will grow like this. So in this manner the cavity is being filled up. But when you talk about geode, it must be subspherical cavity, and cavities are being filled up by mineral. First the lining, then growth of the crystals. Growth of crystals, geode. So from the walls of the cavity inwards, the crystals grow, or through precipitation of the minerals from mineralizing solutions that pass through the cavities. Precipitation of layers of microscopic minerals takes place, and it produces bands, and precipitation of layers of crystals takes place there, and it gives rise to drossy, divergent or reticulate crystals that line the centers of many geodes. This is concentrically arranged layered minerals, and these are called concretions when they grow outward from a central nucleus within the rocky body and incorporate pre-existing mineral matters as they do so. Thus, concretionary aggregates consist of subspherical bodies that include both newly precipitated crystals and pre-existing materials. So, when you talk about concretions, core around which there will be deposition of layers. In case of geode, cavities, subspherical cavities are there, lining, then growth of crystals. Geode. So, concentrically arranged layers that takes place in concretions and in case of geodes. Then oolitic. It presents small rounded concentrical layered sand sized particles which are having grain diameter less than 2 mm, and they resemble a row of fish. As you find in case of hematite, it may be oolitic iron ore, it may be hematite shows kidney shaped kidney ore. So if it is small rounded, showing small rounded bodies, it is called oolitic iron ore. Oolitic behavioral structure is also found in case of aluminous minerals such as bauxite. So piezolytic, it is pea-sized, coarser than oolites, and say gravel sized, as we see in case of graphite, bauxite. So bauxite is oolitic, bauxite is also piezolytic. Scaly crystals are as small plates, as we find in case of tridymite. Stellate, here the crystals radiate as fibers from a common center with a star-like form. That's why it is stellate, as we see in case of wobelite. Tuberous, it shows irregular rounded surfaces that give rise to gnarled or strange root-like shapes, as we see in case of aragonite or phosphorite. Aragonite, tuberous. The structure is said to be, or form is said to be tuberous, irregular rounded surfaces that give rise to gnarled or strange root-like shapes. Plumose, here the crystals present a feathery appearance. There are some minerals which contain one form. Example, chavazite, halite, garnet, all are cubic, but there are others which occur in multiple forms. Ilmenite, corundum, gahalanite, vesuvianite, dactylolite. So they show different types of forms. but there are some other minerals which generally occur in one form, such as halite. Halite is cubic, garnet cubic. Garnet generally occurs as rhomb dodecahedron or trapezohedron. Halite occurs as cube. So, these are the different forms of minerals, that the terms which are used to describe the forms or habit of the minerals. And in my next class, I will discuss about the polymorphism, pseudomorphism, isomorphism. These terms I will discuss. Thank you all for giving a patient hearing to my talk.